Hey everyone, I'm Josh from Pathways Education, and today's STEM topic is derivatives and parabolas. So first off, we'll learn what a derivative is. If you've already heard of derivatives or already know how to calculate them, still stick around. I have a little fun logic puzzle that I like halfway through, and we'll learn about some cool general applications you might have not have known about before. So stick around. First off, the basics. What is taking a derivative? Well, you usually start with a very basic function, x squared, or x to the power of 2, x to the second power. And x to the second power, it's really simple. It's just x times x. And the graph of y equals x times x, y equals x squared, is called a parabola. It's this U shape right here. This is commonly referred to in mathematics and physics. So how do you take a derivative? Well, at least for x squared, it's very simple. And the same concepts apply to take any derivative of a function. So first, you multiply the x term by the power of x. So we had a x to the power of 2. So we take that 2 and move it to the front, 2 times the remainder of our function. And then the second step is take the power of 2 and subtract 1. So x to the power of 2 goes down to x to the power of 1. And we multiply the whole thing by 2. So the 2 goes to the front, and then we take 1 power down. So x squared becomes 2 times x, or 2x. All right, so before we do any applications or practice, let's do a little logic puzzle here. So let's say you're building a staircase out of blocks, and you don't know how tall it's going to be. So you want to find an equation so you can plug in how many blocks tall you need to be, and the equation will tell you how many total blocks, how many total Legos you need to gather to build your staircase. And the answer is going to contain an x squared, believe it or not. And another hint is to try and calculate the area of the staircase. So if you want to pause and try and come up with an equation, you can do that now. And the answer is in 3, 2, 1. All right, so how do you logically find the answer to a problem like this that utilizes x squared in the answer? So if you plot the basic pattern of the staircase, at 1 high, you only need 1 block, 2 high, you need 3 blocks, 3 high, you need 6 blocks, 4 high, you need 10 blocks. So I said a little hint was try and find the area, but it's incredibly hard to find the area in an equation of a staircase, because how would you even go about doing that? But you'll notice if you stack 2 identical staircases on top of each other, like so, you get a rectangle that you can calculate the area of. And the area will help you find the number of blocks. So in our equation, if we say the height of the staircase, for x, it's also the bottom here. And then, as you can see, 1 higher than the height of the staircase, x plus 1 is going to be this side. If you multiply those two together, you're going to get the total area, and then half that total area is how many blocks are in the staircase. So in this example, 3 times 4 is 12. 12 divided by 2 is 6 blocks. Look at that. It works. So we have y, the total number of blocks in the staircase, equals the taller side, x plus 1, multiplied by x to get the area, divided by 2 to get one of the staircases. And when you distribute it out, that, you get an x squared and our answer. So just x squared, as you journey down your math pathway in school, you're going to see x squared and have to take derivatives throughout your classes. So a couple minutes ago, we learned how to take a derivative. Can you take a derivative of these two simple functions. They're slightly different than x squared. A little more complicated, but I think you can do it. So here's the process again. I'll put answers up in 3, 2, 1. Too late. So 3x squared, the 2 you move to the front. So you multiply the 3 by 2, and you get 6. And then, just like in the original example, x squared becomes x to the 1, and we have 6 times x, 6x. And for x cubed, you bring the 3 to the front, 3 times x, and then the 3 becomes a 2, and we have 3 times x squared. So now that we know what a derivative is and how to calculate it, let's look at some applications. So we learned about what a parabola is. It's just a graph of y equals x squared. And if you throw a ball into the air, negating any wind resistance, leaving wind resistance out of it, the ball will follow an exact parabola shape of y equals x squared times some constant. It will follow the perfect trajectory of a parabola. Why does it do this? Well, a derivative of a function tells us a pattern or a trend about the nature of the original function. That's what a derivative does all the time. In the case of a parabola and throwing a ball up, the derivative is the rate of change of that function, or the slope of the line at a certain x value. I don't know what the slope of a line is. It's the amount up that function goes divided by the amount that function goes sideways. So if we look at our derivative of x squared, y equals 2x, and we plot that in a table, we have 1, 2, 2, 4, of course 0, 0. And if you see the slope of our parabola at the red lines, as you can see, the graph comes down, and if the graph were to end here and level out, it would level out at 0. If the graph were to level out at 1, 1, it would have a slope of 2. If the graph were to level out at 2, 4, this point right here, it would have a slope of 4. 4 up for every 1 over, 2 up for every 1 over, 0 up for every 1 over. So that is what a derivative shows the rate of change, trend about the original function. All right, so if the derivative is just the rate of change at a certain point on the parabola, and when you throw a ball up, gravity slows the ball down on the way up and speeds it up on the way down at a constant rate of 9.8 meters per second, gravity. And our derivative, if we instead say gravity pulls the ball down at 1 unit per second, we can see how gravity seems to pull the tip of the arrow further and further down the longer the ball is falling, the longer gravity acts on the ball at a rate that we can calculate by finding the derivative of our function of the path of the ball. Just like this parabola is represented by the function y equals x squared, we can represent this with a parabolic function and find the path of the ball and how fast the ball is going, our derivative. Some other real-world applications of parabolas and their derivatives. If you knew where a basketball player was throwing a basketball from, where the basket is, what location in a 2D graph here, and you knew the apex of the ball, how high it would go, there's only one trajectory the basketball can follow. And if we know all that information, we can model it with a parabolic function that would look something like this, with an x squared at the crux of it. Some other applications: optimize costs for a business. That will parabolic up curve there. Calculate the load at a point on a suspension bridge. There we go, we have a much wider, but still perfect parabola there. Applications can go as far as designing the best shape of a spotlight head. So if we have a perfectly calculated parabola right here, then the light will bounce off and produce the most light coming out of the head. So parabolas and optimization is all around us, and it all starts with basic x squared, knowing how to calculate derivatives. Thank you for watching. If you have any suggestions or questions, make sure to leave them in the comments and we will get back to you as soon as we can. Follow our social media to find out when our newest videos and content is coming out. And don't forget, if you haven't already, to go to our official website, www.guidingpathways.org. Start your journey down a new pathway.